Good morning, good day, and good evening to all our attendees joining us for today's latest Data Science Central webinar. I'd like to start our event off today by thanking Pivotal for sponsoring today's event. Pivotal is a longtime supporter of the Data Science Central community, and we are honored to have them sponsoring our webinar today. I would also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, including Cisco, Tableau, Hortonworks, Oracle, Microsoft, and Teradata, to name just a few. These past webinars are available on demand at datasciencecentral.com, and if you've not had the opportunity to view them, I would encourage you to do so as they do provide some very useful information. Today's webinar is entitled The Science of Segmentation. What questions should you be asking your data? And before we begin, I'd like to just briefly review the format for today's webinar. Today's event will be approximately 1 hour long. We have 2 panelists that I'll introduce to all of you in just a few moments. We should have about 10 to 15 minutes for a Q&A following the presentation, and this event is being taped and will be made available later on this afternoon at datasciencecentral.com. I'd also like to encourage our attendees to provide questions throughout the presentation. We will be reviewing them and presenting them on your behalf during the Q&A portion of today's event. My name is Tim Matteson. I'm one of the co-founders of Data Science Central, and I'll be your host for today's webinar. I'm very pleased to introduce today's speakers, Grace Gee and Jarrod Vawdrey of Pivotal. Grace is a data scientist with Pivotal, where she is focused on helping retailers transform into data-driven organizations. She has a master's in science in electrical engineering from Stanford University, where she focused on machine learning and artificial intelligence. Her recent education at Stanford has ignited her passion for big data analytics, particularly in their application in real-world problems. Jarrod is also a data scientist with Pivotal. His professional experience has been centered within marketing and customer relationship management, analytics preparing, analyzing, and modeling data for a wide range of business applications. He received an undergraduate degree in mathematics from Kennesaw State University, additionally studying statistics and business. He also finds technology integration to be fascinating and enjoys making different tools work together. So welcome to you both, and we're looking forward to your presentation. Enterprise companies starting the transformation into a data-driven organization often wonder where to start. With the rise of big data and big data technologies, additional sources are rapidly becoming available. In order to effectively utilize both traditional sources and new ones, companies first need to establish a data lake to bring all their data sources together in a single analytics environment. One of the first data science projects worth exploring is segmentation, which automatically identifies patterns. In today's webinar, Grace and Jarrod will discuss what segmentation is, traditional approaches to segmentation, how big data technologies are enabling advances in this field. They will also share some stories from past data science engagements, outline best practices, and discuss the kinds of insights that can be derived from big data approaches to segmentation using both internal and external data sources. So with that, Grace, I believe you're going to start us off this morning. You can begin as soon as you're ready to go.
Great. Thanks for that great introduction, Tim. Thanks, everyone, for joining us today for this webinar focused on segmentation. And before we dive into the details of what segmentation is, we'd first like to level set by beginning this webinar with just a few minutes of discussion about the types of big data technologies that are needed to enable segmentation on today's big and growing data sets. Then after that, we'll talk about what segmentation actually is and how it's used across industries today. And finally, we'll walk through a use case and guidelines we use to help companies incorporate segmentation into their own data discovery processes and business decisions. And also throughout this webinar, we'll be providing insights into what questions you should be asking your data. We've worked with a lot of people who are in the midst of transforming their companies into a data-driven organization. And as you can imagine, and as you've probably experienced yourselves, this is a major, sometimes overwhelming task. And a lot of companies that initially come to us struggle with where to even start. So we often hear questions like, how do I make my data available for my analysts? What tools are needed to efficiently process and build models on my big data sets? What data should I be collecting and archiving? How do I leverage data to generate value for stakeholders? How do I enable analysts and data scientists to become more effective? Ultimately, what these companies are trying to do is understand where and how can I start to use all of my data to quickly gain actionable insights and begin integrating data science into our own organization's practices. So as part of their transformation and transition to becoming big data analytics generators and consumers, these companies often encounter similar business challenges around enabling data availability and agile analytic workflows. In nearly all of our engagements with these types of companies, we see that their data is siloed and scattered across multiple organizations, and sometimes over multiple platforms. And that makes data integration especially difficult and time-consuming. We also often see companies struggling to find and collect enough data for the big data analytics projects they want to execute, either because they were limited by their current platforms or own ETL processes in terms of the amount of historic data they can actually store, or they simply just didn't have access to data like detailed consumer profiles. Finally, because of all of these data issues, organizations struggle to verify and trust their data and are confused about which is the single source of truth. So, for example, we commonly see disagreement amongst business groups over something as simple as defining the number of customers who purchase items in a certain time period. And we also see different calculations across different business units for valuable metrics like internal revenue, which leads to confusion about which numbers to trust and which numbers to use for modeling predictions. And data issues aren't the only problems we see in organizations that are early in their big data analytics journey. Oftentimes, their technologies and even their organizational structures are prohibitive to implementing an agile and iterative analytic workflow. Often outdated analytics architectures that are focused on optimizing operational processes and reporting actually hinder the experimental, iterative nature of big data analytics, requiring data scientists to go through a long and sometimes complex process just to access the data they need and forcing them to move their data to their own desktops to analyze in a safe development environment. We also usually see a knowledge and skills gap in terms of understanding what technology and tool sets are available and feasible for working with a company's big data sets. And finally, just the company's organizational structure itself can often inhibit fast acquisition of data, forcing data scientists to go through the IT org or other data owners to access the data they need, as well as inhibit the communication of insights if the data scientist doesn't have sufficient access to business stakeholders to quickly communicate progress and insights, as well as collect feedback and use it to iterate on their own models. So in our experience, when we engage in a data science project with our clients, we ensure that multiple business groups are brought together to share relevant sources and agree on measurements and calculations of features, which in the end provides a lot of added value, especially since typically these groups never talk to each other due to an org structure that inhibits the spread of information and collaboration on analytics. So to reduce these types of common business problems, there are two main technologies that we think are really important for organizations that want to be big data analytics leaders. And these are the data lake and what we call the agile analytics platform. So a data lake is basically an efficient, massively scalable data storage platform where all data owned by the company should land. It should store all the data the company ingests, regardless of the source, since we don't know what data we might need for future analytics projects. So we just want to make sure we don't throw any data away and possibly inhibit our ability to answer future questions. A data lake should also be able to store any type of data. So it should be able to be structured, unstructured, or semi-structured. And since we might not know immediately what optimal form the data should be stored in for future analytics, this is a really important aspect for a data lake. So in general, the data lake should provide a single centralized source for any organization to access the data they need, no matter what kind of data it can be. And then integrated with this data lake, there needs to be an agile analytics platform where the data science work can actually be done. And so an agile analytics platform should be a technology stack that was purposely built for big data analytics. So it shouldn't just be some analytics software that piggybacks on the existing reporting architecture that often prioritizes operational apps first and ad hoc analysis last. So ideally, this Agile Analytics platform should be some sort of distributed computing platform that can compute on big data in parallel and in place. And that way, no data sampling is required or forced by limited memory. No data movement is necessary, and analytic algorithms can scale as the data scales. So this is what a data lake and Agile Analytics platform might look like, and exactly the type of architecture that our own data science team has the benefit of working on every single day. So first, a Hadoop distribution is what's commonly used for the data lake component, where all the various structured data is made available. And here it's represented by Pivotal HD. And then we as data scientists access and manipulate the data during our data science workflows through an MPP database like Ransom Database or a SQL query engine for Hadoop like Hawk. And our data transformation, feature generation, and machine learning functions we use are made available through a variety of mostly open source analytical toolsets like MATLib and procedural languages like PLR or PLPython. If real-time analytics were important to us, we might also consider using an in-memory database here represented by Gemfire. And if we want fast in-memory iterative processing, we can also leverage things like Spark and MLlib. So all of these components make up the big data platform that's vital for companies if they want to use data science as a differentiator. Now, the first step for companies to integrate this leading technology in their big data analytics workflow is to connect and feed in their own internal structured data, here represented on the left. But with today's explosion of data and increased data availability through APIs and third-party services, much more data can actually be collected and leveraged for all types of analytical work. So with the data lake, companies should have no trouble saving their unstructured and semi-structured data in the same place as their structured internal sources. They can also take advantage of external data sets to augment their own data sets and add new value or insight. So for example, they can form agreements with their partners to share data. They can harvest data from the web and social media networks like Twitter. They can purchase market and competitor data from sources like Nielsen. They can collect government data like Census and weather information. And with increasing interest in the Internet of Things, there's also tons of sensor data now available. So we can get data for tracking things like quality assurance or delivery efficiency. So using all of this data within a data-driven platform that we've shown here, companies are now able to not only serve operationalized reports and applications, but they can now also accomplish big data-driven projects like inventory optimization, demand forecasting, fraud detection, and what we're going to be talking about today, segmentation. So now that we've talked about the technologies you need to effectively use big data at your company, let's actually dive into what segmentation is and how you can use big data and the right technologies to automatically find patterns and segments in your big data sets. So what is segmentation? Segmentation is basically an automatic grouping of entities based on a common set of features. It's often used to identify and find patterns among similar entities. And the great thing about segmentation is that it is a truly unsupervised, data-driven learning technique without any preconceived notions about what the grouping should be. Now that there are so many rich and big data sets available, using a method like segmentation becomes all the more necessary to find many, many segments using high-dimensional features. And we see segmentation used for three main reasons. So the first is identifying features that greatly differentiate groups of entities. So for example, segmenting high-profit suppliers versus low-profit suppliers, and trying to identify the differing behaviors in order to understand why certain suppliers might be underperforming. We also see segmentation used to try to identify similar characteristics across different groups of entities. So for example, this would be used to pinpoint potential cross-sell or upsell opportunities amongst different segments. And finally, we also see segmentation used to try to predict characteristics and behaviors of new or unknown entities. So for example, when a retailer is trying to introduce a new product to the market, they might try to identify which product segment this new product is most like and try to infer a similar type of market response. The segmentation problems these days often deal with a few main issues. These include things like trying to aggregate multiple data sources from multiple lines of businesses, including external sources, using big data sets, particularly from sensor data and transactions and point of sales, which generate huge data sets, and also dealing with high-dimensional feature sets because of all of this data that's actually available today. And segmentation is more like an art than a science when you're trying to select the optimal number of clusters and discovering which features to focus on, which is why it's pertinent to have the right technologies that enable faster iterations for the experimental nature of this type of work. So you need a data lake to be able to access and use all of this data available, as well as a distributed computing platform like MPP databases or Hadoop with Hawk to feasibly compute on all of this data in an efficient, parallelized manner without requiring any sort of data sampling or data movement. And particularly segmentation is truly a case where sampling doesn't make sense. So we want to ensure we can use all of the data. And of course, there are several machine learning libraries like MATLib that are available with super helpful functions and clustering algorithms to do things like segmentation. So now that we've had a brief introduction to segmentation, let's discuss some common use cases and data sets that are used. So as I've mentioned, segmentation is a super great tool for helping you understand your data and automatically finding patterns within your joined data sets. And as such, segmentation usually pops up in a ton of different verticals and industries. So some common instances where we see segmentation used include customer micro-targeting. So this is where we're trying to identify market segments and their purchasing behaviors and preferences. Segmentation is also used in operations and logistics, like trying to identify behaviors of stores, suppliers, delivery services, and others in the supply chain, and trying to understand why certain ones are outperforming or underperforming. Segmentation can also be used in fraud detection, so trying to identify anomalous user behaviors within networks. And it can also be used for entity or domain resolution by trying to infer missing labels or groups of similar entities, like trying to map groups of web domains together. So let's just take that first use case, micro-targeting of customers. So in this example, a vast number of data sets can actually be used to help build consumer profiles for segmentation, as well as to cross-check purchase behaviors with supply chain operations like inventory management. So for customer segmentation, some valuable data sets might include customer demographic profiles, which might have been collected through membership or loyalty cards, or consumer surveys or online profiles. Sensor data from supply chain operations, like shipments and inventory. Product metadata, like assortment or sizing or packaging of products. Shipment data and store metadata, like the store size, its layout, display of the products within stores. Transactions and point of sale data, of course, to get the revenue and price. Delivery information, like the distribution centers. Marketing plans, like promotions and coupons. And external data sets to help add value or augment missing data, like using Census for augmenting consumer profiles, Nielsen data for market and competitor information, and even social networks for consumer sentiment. So to continue our customer segmentation example, often companies don't or can't collect sufficient data about their customers to construct a complete profile and really try to understand them. And this is a prime example of where external data can actually be leveraged to augment their internal view and make what was once data of little value into rich features that can be effectively used for segmentation. So there are a vast number of external sources available now for almost any kind of data you could want, like Net for social network streams or Forecast.io for weather data. And using these external data sources can help companies develop a 360 view of their customers, gain insights into how their consumers are interacting with competitors, improve the accuracy of their predictive models through a larger and richer data set, and increase the value of their internal data by using external data to fill the gaps. So one particular example of this is using census data to build more complete U.S. demographic profiles by geographic region. So let's say a consumer packaged good company or CPG company is interested in better understanding their target market segments to improve their marketing strategies and supply chain planning. But not only are CPG companies interested in the individual consumer, but they're interested in the family profiles as well. So for example, consumption of child products or household supplies like laundry detergent are most likely affected by family size. In this case, CPG companies can use external data sources like the Census public use microdata sample files, which has person records and housing records that can be merged, to build rich family profiles, like estimating the number of households with children of a specific age range, or mapping the socioeconomic status of family groups. So now I'll turn the webinar over to Jarrod, who will walk through a segmentation use case and explain best practices for segmentation projects.
Hey, great. Thanks a lot, Grace. That was a great level set there on the enabling technologies and introduction to segmentation. So as you just mentioned, now I'm going to discuss a typical approach to segmentation and kind of frame that using a real-life use case. So at Pivotal, we typically use a four-step process when approaching a segmentation project. Starting off with a data step, this is typically where a lot of the heavy lifting happens in a project, and we spend a lot of our time. Even in an MPP database, there's a lot of iteration and heavy lifting that needs to happen here in terms of identifying join relationships that may or may not have existed in the past. Thinking of the use case where we're breaking down silos or data that has not been joined together. Sometimes there's some iteration that needs to go on there in order to identify those joins or even connect together additional tables which will establish those joins. And also aggregating the data to a common granularity. So think of the case of identifying a consumer within the data warehouse at a specific point of time and prepping the data into a structure that allows you to kind of model that individual consumer at that point. The next step here is the feature step. And here we're engineering or creating a set of characteristics within the database that represent or profile the individual, say consumer in this case, and their historical behaviors. So think of examples such as age, gender, time since last transaction, average time between visits, and sometimes these can even become quite sophisticated, such as, say, in the case of sensitivity to price change. This might be a value that comes out of a model on its own, right? The next step is the model step, and here we're doing both a selection of which algorithm is appropriate for the project and data that is available, and then also actually running that model and kind of dialing it in to make sure we're getting the most value from the data that's available. So some candidates here could include such as k-means clustering, hierarchical clustering, even regression approaches where we're, say, then grouping the coefficients. A lot of companies we actually see kind of stop here, right? And you go through this process of then kind of presenting the clusters to a business group, which then you go through the exercise of kind of labeling those with some crazy labels and then coming up with some business rules which then establish these segments moving forward. And potentially there's some results that end up in KPIs moving forward that the business tracks. However, we've found a lot of value in actually kind of following up with this additional step here, really analyzing the results that are coming out of the cluster beyond just, we've now assigned some labels. So some of the metrics or analysis we look at here, looking at the average of each individual feature across clusters after normalizing, look at average cluster features versus the population average to find, where certain characteristics are standing out for an individual group, and then also identifying commonalities amongst segments. So we'll discuss that a little bit further here as we kind of dive into a use case which will help kind of frame this four-step process. All right, so as an example, we're going to go through the objective of identifying characteristics of a consumer that, say, prefer certain brands or products, right? And this is a very common exercise that at least pivotal customers go after because there's really an understanding of, hey, we want to create more value for our consumers, and in order to do that, we want to have a good understanding around their individual preferences. So Grace has already called out a couple of these, but typically there's some common business challenges that you come across. The first being often companies have siloed data. So think in this example of consumers, we may have point of sales data or transactional data that we're collecting actually at the register. So think about the kind of receipts that you get when you check out on a place that have, the list of the few items that you've purchased. We combined all these together, which is what the retailers are doing on the back end, or the different customers doing on the back end. We come up with these point of sales transactional data sets, which are typically quite large in size as they're at the line item level. Another organization within that company may also be collecting, say, loyalty data from a loyalty card. While it might seem like these two systems should be very well connected, even sometimes right when you're scanning your loyalty card on the back end, that's not really a safe assumption to make, because a lot of times the point of sale system is something that's being set up very early on for operational type activities, whereas the loyalty system may be something newer that was kind of appended on to the internal systems at a later date. We also see things such as demographic data and third-party data appends, which may come into the system, which is also you can kind of think of as a siloed source there. So these are common business challenges. How do you actually join all these sets together? Also, typically, internal data may not be sufficient enough to actually build an in-depth profile. So if we think about the use case here of preferring certain brands, well, it could be the case that your consumers do not actually have the strongest preference towards your brand or product. It may actually be competitors. So how do you try and capture that information and make sure it's included in your model so you can act on that? And this last bullet point here may seem like something really simple, but a lot of times we don't actually have a good idea of which consumers are more or less profitable. And the idea here is we really want to focus on those customers which are creating the most value today or have the propensity to create the most value in the future. It's just an easy way of filtering and making sure we're creating the most value from our modeling effort. One of the added benefits of using a segmentation is we're actually including all the consumers in to our modeling effort, and therefore, this decision-making process on the front end is not as strong, but it's definitely something to keep in mind as we kind of start communicating results and so forth to the business. So many data sources could come into an exercise like this. We just discussed point of sales and loyalty. Demographic data can come in all different types. Census data is something that's publicly available. There's also a lot of vendors which actually sell data append, and these can include things such as upwards of 50 and 100 different characteristics on consumers, which through feature engineering you can expand on, which we'll discuss here in a minute. We also might have different data sources such as product and store metadata. This is important, right, if we're understanding what the preference is to a certain brand or product. We want to kind of go beyond just the label of that brand or product. We want to actually understand what are the characteristics and the features that make that product, right? Then finally, external data. So, one easy thing to think about, right, is it's raining where I am in Atlanta, Georgia today. Weather is like a great external data, especially when dealing with consumers. But as you can imagine, there's lots and lots to use there. And the idea is we want to start kind of controlling for differences and understanding kind of external factors which are helping to influence decisions. Okay, so once we have our kind of problem defined here, now we go on to kind of step one, which is the data step. So as we just discussed, the kind of first phase here is identifying the relationship and joins among kind of data sources. In some cases, this may be really straightforward. There might be a nice ID within the data which identifies consumer across time. But kind of in the real world, what we typically see happening is, a consumer may have many IDs collected at different points of time. Think, like breadcrumbs that people are dropping as they interact with different areas of your business. Not always are these collected together, so there's various approaches that you can kind of take in order to identify these. And in some cases it might be matching on, say, names and addresses, using some kind of fuzzy matching to kind of take into account the ambiguities that might exist with entry errors and moving and so forth. We've even gone as far as using, say, graph theory to understand kind of what are the links of people if we see, say a name and a birth date exists here, except we see, say, an address move. Can we kind of track your information across those kind of one or two step jumps that may be apparent within the data? Kind of the big kind of takeaway here is it's not always straightforward, right? And we can spend 80 and 90% of our kind of data prep time, modeling time in the data phase and not being super effective and coming out with not a lot, or we can spend that time really iterating and diving into the data. And so something like an MPP platform like Greenplum or Hawk that the pivotal data scientists are using day to day allows us to go in there and kind of use those brute force, very iterative approaches to kind of identify these relationships. And the next step is kind of cleaning the data. So it's not always the case that we go in and we have pristine data. A lot of times there is outliers. There could be just due to entry errors, errors in the systems themselves. And so we want to make sure that we're taking care of these, either by removing them completely, that consumer completely from the modeling exercise, or just actually removing that value and then imputing something or in such as the median or weighted average into that empty space now. Then we move to kind of the aggregation and selection of the data in a way that makes sense, right? So you can think of in the case where we have consumers, they may be interacting with your business over time. We may only just want to look at one snapshot. So for instance, one point in time for all those consumers. And this is kind of the stage where we identify where that takes place. That's a pretty simple example, but you can think of a case where we actually want to model our consumers at a different point in time, maybe to capture something as a life event change, right? So in that case, it might end up where our keys become something more than just consumer. We might say a consumer date tuple becomes our key. And so really here we're trying to understand that. And how we kind of make that finalized decision is doing a gap analysis. And here we're trying to determine whether the data at the aggregation that we've decided on actually supports the future analysis or the segmentation modeling. So not always is the case where we're able to kind of identify at the consumer level. And so you might think in that case we might say roll up or aggregate up to a geographic level, such as zip code or census tract, in order to make sure our data supports that. There's also the case where the internal data is just not enough, and so we might actually go then and iterate back around and search for more external data, which will either make the internal connections or augment the internal set enough to move forward with the analysis. Okay, step 2, feature engineering. This is where things get very, very exciting. So once we have all these data sources together and linked up in some fashion, kind of the next phase is we want to develop a very in-depth and detailed description of each consumer in order to understand what their preferences are. And so how we do this is we actually take these tables and almost reverse what typical data-based engineers are doing and denormalize the table and create a single, you can think almost huge flat table where each column is now a representation or a feature which describes that consumer which lives in that record. And so we have some kind of high-level examples here. If we look at the blue bucket all the way to the left, transaction and point of sale type features, we see total sales here. So this itself can blow out into many, many features or columns within the table which represent characteristics. So we can think here could be total sales over a certain period of time, the change in sales, And we could alter and change those kind of parameters there and think, what were the total sales in the last 30 days? What were the total sales in the last quarter? The last couple of years? And so very quickly, each of these kind of high-level descriptors can filter out and become, tens to hundreds to sometimes even thousands of different features. Why is that important? Well, really, we're trying to paint a very, very detailed description of each consumer here so we can understand what are these differences and what are these kind of data-driven groupings. If we don't have full coverage there, we're kind of somewhat biasing our end results. So, within a recent lab that we just got out of, we actually created over 300,000 features to push into a modeling effort. So you can kind of get an idea of the scale that these big data platforms allow you to kind of expand at very quickly. A few other examples here, you might include something such as weather, right? Purchasing behaviors significantly different when the weather is hot outside versus cold. Those are the kind of insights that we can derive from those kind of features. Again, we want to really describe the products that you're purchasing in a lot of detail so we can understand what is kind of driving that preference towards those products or brands. Demographics, these are always great in order to understand the kind of consumer and paint a really visible picture in your mind, but we find a lot of times the kind of behavioral characteristics are often the ones that are more or differentiate groups more. Also, and finally, if the loyalty is available, things like status, length of membership, activity, all play in very well into a segmentation type exercise. So the next step, or the next phase within step 2 is now we have this huge feature set. Well, we don't want to just include everything, right? If we do that, we're going to end up with some unwanted bias due to the inclusion of, correlated features, right? At this stage, we want to kind of filter this set down and find the kind of core individual set that we're then going to start feeding through and testing in our modeling exercise. So we have listed down a couple of approaches that we have had success with in the past. The first being principal component analysis. Here we're calculating a reduced set of linearly uncorrelated variables, which account for as much of the variation in the data as possible. So you can imagine we can set some threshold and just capture the first set of principal components, which then end up feeding into the follow-up modeling exercise. Another approach that we're able to test, which is totally enabled by the kind of high-performance environments that we're in, is actually just doing a kind of correlation across all pairs of features, and then kind of going through with a very iterative approach and excluding the highest correlated feature and kind of going through that process there, iterating until we've hit some predefined threshold and no correlated pairs exist. This allows you to kind of get a little more manual in the process. As you can imagine, with each iteration, you can have a decision at some points of which out of a pair of correlated features, which to remove. This, again, is something that's totally enabled by the environment themselves. As you can imagine on say a traditional type tool running pairwise correlations over 300,000 features is probably not going to be something that you can kind of fit in, given that we're mostly working under time box kind of engagements here. But in an MPP or a Hadoop type environment where you're able to very quickly go through this. Then on to actually step 3, where we're selecting the model algorithm and actually building the model itself. So in this example, we're going to go with k-means clustering. This is typically a safe first kind of approach to work through. And here, again, this is a very iterative algorithm. It starts off with a set of centroids, which then each individual consumer or their values are assigned to. The centroids are then recalculated based on those new groupings, and the process goes on until we find or hit some kind of threshold. One kind of question that often comes out of this, right, is how do we come up with the number of initial centroids, or how do we define what K is? again here within the kind of big data environments or these highly performant environments that we're working in, the platform actually allows us to iterate many, many times over many different models. So here what we'll do is actually select a range of Ks, and then for each K run several models or K-mean clusters at each level, and then calculate a metric such as, say, silhouette coefficient to understand how well fit that model is to the data. Doing this very iterative approach, we're able to then go through and kind of select which one comes out the best. As Grace kind of called out earlier on, it is somewhat more of an art than a science. So this makes even having a high-performant environment where you can iterate many times and kind of view the output yourself and kind of analyze it before iterating again is very, very powerful. It takes away from the having to really make all the decisions up front and run a modeling that may take, say, a couple of days where you only have one shot at it, right? Here we're talking about running hundreds, if not thousands, of K-means clusterings to identify the best. Once we have the output, then we go and kind of look at the features within and across segments to identify what are the kind of key characteristics of each grouping. Looking at these, we can make this kind of decision around which is best to proceed forward with. So as mentioned earlier on, this is typically a stage where we see a lot of customers have just stopped. They take their labeled customers and then move forward with defining some high-level business labels and some business logic, which they'll then move forward. So they think, say, ages 18 through 25 exist in this bucket, 25 through 30 live in this bucket. Typically what comes out of our exercises, though, is we've included a lot more features in the front end. And typically our K, because of that, is a lot larger. So we're typically moving towards what people call micro-segmentation. So in these cases, the step 4 is very, very valuable and important. So we have one visualization here, and essentially what we're displaying is how we're actually looking at. So we've taken each individual feature, taken the average within that grouping, and then normalized these so we can compare across various clusters and see what are kind of popping and what are not popping and defining that individual grouping. So some of the value we see come out of this kind of visualization is identifying cross-sell and upsell opportunities. So it's quite often you'll see two clusters that share a lot of the same characteristics, but one may be purchasing an individual brand or product where the other is not. So in this case, right, it makes sense that the cluster that looks exactly the same but is not purchasing may have a higher propensity to then go ahead and purchase that product. So out of that, we definitely shed some insights into where a follow-up step could be in defining what those true recommendations are. Another insight that typically comes out of these is identifying data quality issues and also issues that come up from operational activities. So we'll see such thing as disproportionate number of our inventory being assigned to an area where it over-indexes with a certain kind of grouping. So in this case, basically the clustering would show that this grouping actually requires more inventory there, or it could be the case that the data is not appropriate within that area. So we've uncovered something such as, say, missing inventory counts there. So these are just a couple of the examples that come out of this final step. But you can imagine here there's a lot of kind of follow-up analysis that we can go through in looking at these huge set of, say, a few thousand features and kind of going through and filtering and understanding what are the similarities, differences across groupings. So that's kind of where I'll leave the segmentation use case up at this point. One of the kind of pieces that come out of the added value that comes out of this exercise is that we've kind of developed this very rich, reusable set of data assets. So what this allows you to do is then take the insights from this clustering exercise, such as, say, the cross-sell upsell opportunities, and now incorporate these additional features into the follow-up modeling effort. So just to summarize what we've discussed today, We believe segmentation is a great place for companies to start because it helps to actually uncover a lot of these questions and in a lot of cases actually answer these questions, which are important to establishing the foundation of a data-driven enterprise. So are you collecting the right data and storing it in the right place? We would have uncovered an answer to that through this exercise. Do you have the right technology to support your data and data science endeavors? We would have quickly found that if we had the right technology during the data step early on, right? Where are the gaps in your data? How can external sources fill those gaps? So were there any questions or hypotheses that you had going into this exercise that you were unable to answer? And how can your data sources be joined or aggregated together to build a rich feature set? This would have also been answered during the early on stages of the segmentation exercise and hopefully answered, right? And how can you extract business value from your data? Typically, we see a lot of value come straight out of the segmentation exercise, as we've shown up in the previous slides. So segmentation will help you answer all of these questions. And with that, I'll pass it back over to Tim here. Thank you very much.
Okay, great job, Jarrod and Grace. Really very interesting presentation and very useful as well. So with that, we are at our Q&A portion of today's presentation. While we're during this period of the webinar today, you'll all see that both Jarrod and Grace's email addresses is visible. I would suggest that you take it down and you can contact them following today's webinar if you have additional questions. So we have lots of questions coming in. Several questions to start with have centered around this wanting clarity, I think, with regards to the relationship between clustering and segmentation. For example, one of the questions was, while clustering is only one way to segment, would you say that all clustering is segmentation? So if you can clarify the relationship and kind of go into more detail, I think that might be helpful.
Sure. I wouldn't say necessarily that clustering is segmentation, and Jarrod, feel free to jump in with your own opinions as well. I see more so clustering as an algorithm that can be used for segmentation. So clustering is used in a lot of other things outside of segmentation, right? Like just in general, just trying to group things together. It's usually used kind of as a pre-step before you want to run some other algorithm on your data, as some sort of data aggregation measure as well. So I kind of see segmentation more as a use case and clustering as a way to approach that use case.
Okay, very good. Jarrod, are you okay with that? Do you want to provide anything?
No, that's, but yeah, perfect answer, Grace. I would have, 100% agree.
Very good. The next question is, can segmentation be used in real time to identify changes in established groupings of entities? I guess, for example, monitoring of manufacturing operations, for example.
Yeah, so that's a really great question there. There's a couple approaches that we see. The first, and being the most simple, is actually training the segmentation model in kind of batch or offline. In that case, you'll come out with a set of, say, we take the K-means example, a set of centroids, which as data is kind of streaming in on new data, we can kind of assign those new data points back to those initial centroids and get an understanding of how they squeeze into that existing model. There are also a lot of online clustering or segmentation approaches where you're actually training the model as new values are coming in. And so in this case, it's true that, or it's possible that your segments will actually change over time as more information becomes available. So in both cases, yes, it's possible to kind of identify any anomalies or others that are not kind of clustering into a grouping in a satisfying way.
Okay, very good. Thanks, Jarrod. The next question is, how do you handle two common problems with the source data, identifying unique individuals and unique companies?
Yeah, so this again is a really interesting problem. So in a lot of cases, what we find is when we're kind of merging data from across multiple sources is our customers will have a pretty good idea of how to identify, say, a customer within one particular source. So they might have an existing ER diagram or some data dictionaries that go into detail around that. So in that case, we'll typically work off that predefined set and then merge in the additional kind of sources from other organizations into that and essentially try and capture like fields. So, the ID may exist in one source, however, in the new source we only have such an address. So we would try and merge in that address to then basically carry over the key into the new source. As I mentioned, this is not always possible. We think of the example of, say, social media and trying to merge kind of open source Twitter data in with your individual accounts. It may not be possible to actually make any connection within the middle. And so in those cases, what we typically end up doing is aggregating one of the sources up to a level that then can be merged in. So, do these tweets, are they geocoded? Can we kind of aggregate that up to, say, a zip code level or a city level and then merge in at that stage and then carry through those kind of aggregated features at that point? From there, it can get very, very complex. Again, we've tried things as far as using graph theory and so forth and fuzzy matching, but those are typically the kind of first two approaches that we'll take.
Very good. Thanks, Jarrod. Next question, is the multi-nominal logistic regression technique a good approach for modeling segmentation?
Yeah, so in that case, you'd have to have some predefined labels. Sorry, Grace, go ahead.
No, go ahead. You're already on the roll.
Yeah, so we've kind of described unsupervised learning today, so we kind of come up with some data-driven groupings where we don't have any kind of predefined notion of what those groupings should be. In the case of a multinomial regression, that's now supervised, so we would have some pre-existing labels that we would then go out and train up against. This is also a very, very powerful approach if you have those labels existing, right?
Okay, great. So yeah, I'll let you guys field the questions, whoever feels the most appropriate, and you can both chime in as well. So with this next question, what is the extent of information lost when you use PCA?
So that's really dependent, on what the data set actually is, because, for example, PCA doesn't, or other dimensional reduction techniques don't always lose information. So sometimes you can actually be able to reduce your feature space and actually get back to the same high dimensional feature space using a dimensional reduction technique without losing any information. For example, if you can create one of your dimensions as a linear combination as the other in the most simplest case. So it doesn't always lose information, but in the case that it does, the great thing about PCA is that it's really useful for picking out, the kind of dimension that is the most important in differentiating across features. So that's why it's a really useful tool for kind of reducing your feature set, especially for segmentation exercises.
Great, thank you, Grace. And I think you touched on this, and this is a good follow-up question, I think, in your presentation, Grace. What type of ingestion framework is used to address all of these different data formats?
Yeah, that's actually a really great question. And at least at Pivotal, our data science team, we work closely with our data engineering team, who are really the experts in how to build the right architecture to ingest all the different types of data sources that you need, so that we can actually do our data analysis on it. So there's things like, if you're using Hadoop, for example, as your data lake, there's lots of different libraries and packages you can use to ingest data, like Flume or Scoop, which is kind of more of a command line interface. And Pivotal, we also kind of help spearhead, Spring XD, which is kind of what we describe as a distributed extensible system for doing any sort of data ingestion or kind of batch processing and analytics. So for example, you can use Spring XD to create a stream to kind of monitor a Twitter feed and pipe it directly into a file on your Hadoop system. So there's lots of different types of tools out there in order to help you ingest all these different types of data sets.
Okay, thank you, Grace. Next question is, how do you combine categorical and continuous variables into a single cluster analysis given their different scales?
Yeah, so this is Great technical question. So yeah, this is something we're actually still experimenting with a lot, and I don't think there's any one great answer. You've already kind of highlighted one of the most important factors, and that's kind of rescaling all the features so that they're on a similar scale, whether that's through normalization or standardization, so 0 to 1, or meaning out everything at 0 with a standard deviation of 1. There's also other metrics that you can use actually in the distance portion, which can potentially help that as well, say using a median instead of a mean. However, in all those cases, there's really still no appropriate way of then also including in, say, a categorical number, which is just a 0 or 1 representation. So one thing that we have found is it's best to kind of stick with one or the other. So if you have a lot of categorical variables, to try and transform some of your continuous variables as well into categorical, maybe through, say, discretization. And that would just kind of keep everything standard. On the other approach, we've also seen taking the categorical variables and kind of turning them into percentages or applying some other transformation in order to get them into the model. So not a great answer there either way. Definitely something we're still experimenting with on our side and trying to come up with a optimal approach, right?
Oh, very good. Thank you, Jarrod. The next question is, if we use k-means, how do we decide the value of k for a problem? Can we use categorical and numerical data at the same time with k-means?
Yep, so I think Jarrod kind of mentioned the last part of that question just now, but in terms of trying to, decide, what the optimal number of clusters are, trying to decide k, that's a really great problem and something that you do have to kind of, how we kind of said, kind of more of an art than a science, really trying to figure out what the number of clusters and what sort of feature sets you want to use for k-means. So as Jarrod kind of mentioned during our model building procedure, specifically for k-means, what we usually do is we run lots and lots of different k-means for lots of different values of k. And then we basically use some sort of measurement. There's a lot of research out there trying to figure out, how best to measure how good your clustering is. So for example, since we use MATLAB a lot, MATLAB provides this measurement called the silhouette coefficient, which you can look up, and it basically measures, how close your cluster's points are to each other with relation to how far your cluster's points are from other points in other clusters. So there's that sort of measurement called the silhouette coefficient. And so what you want to try to do when you're measuring the silhouette coefficient of your resulting clusters is you want your resulting clusters to have a silhouette coefficient as close to 1 as possible in order to get the optimal clustering according to this type of measurement. And so when we try all our different types of Ks or number of clusters, we basically plot what the silhouette coefficients are and try to choose the best one. So that's one way that you can go about choosing the optimal number of clusters.
Great. Thank you, Grace, for the additional details. I appreciate it. Next question is, we always are talking about and bantering around big data, but maybe you can go into more detail in terms of the typical size of a data source that is incorporated into any given segmentation exercise.
Yeah, that's a really great question too. So I personally work with a lot of retail data, and so specifically in retail, there's huge data sources from the transactions and point of sales data as well as the inventory data, because in those types of data sets, retailers are usually tracking per scanned item, per day, per store. So depending on how much history you're looking at, even if it's just a few years, you can get billions and billions of rows and records of data, which end up being terabytes and terabytes of data. So trying to aggregate that data and make sense of it and build features out of it, can be time consuming if you don't have the right type of architecture, which is why we spent so much time in the beginning of this presentation describing the type of distributed architectures and data lake that's really necessary to really work with this data in an efficient manner, where you can actually use all of it to do your modeling. And Jarrod, I don't know if you want to jump in with any of your own experiences.
No, you hit it on the head there. I mean, I'm just thinking back to my a recent engagement. I think our final prepared feature set ended up with 50 million records and the 380,000 features before we went through feature reduction. So it's kind of an idea of the prepared set, and that was narrowed down from, just as you mentioned, the billions of record kind of transactional level data. Yep.
Very good. So huge data sets on occasion here. So I'm sorry, but that's going to have to be the last question as we wrap things up. I want to make sure that everybody that has answered or asked a question knows that all these questions are going to be sent to both Jarrod and Grace so they can follow up directly with you. There's an awful lot of interest and lots of very good questions about the segmentation portion of big data. So rest assured everything is going to be sent and they'll be getting back to you directly. I have just a couple of quick announcements to make. To please mark your calendars for April 28th in our next Data Science Central webinar, The Beautiful Science of Data Visualization, sponsored by Tableau. Also, as I mentioned earlier, this webinar has been taped and will be made available later on this afternoon at datasciencecentral.com. This brings our webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions, and a special thank you to Pivotal for their sponsorship, and to our panelists today, Grace Gee and Jarrod Vawdrey, for their insight and great presentation today. My name is Tim Matteson. It's been a pleasure being your host for today's webinar. I'll look forward to seeing you all again on April 28th.